Welcome back, everyone, to this episode 5 of The Blind Spot with Marcelo Gleiser and Adam Frank, and yours truly, Evan Thompson, in Aarhus right now. And this is our part 2 of the discussion of cosmology. And just to quickly recap what we talked about last time, we talked about general relativity, how that specifies the expansion of space-time, and how the standard model of particle physics specifies the evolution of matter. This is for the very first tiny time intervals after t equals 0. And there are some issues about t equals 0 that I think we're going to talk about today. And is there anything either of you would like to add about the last discussion before we launch into modern cosmology and the early universe?
Yeah, just where we stopped, right? So we stopped at when the Big Bang Theory was vindicated as the most, or the best, let's put it that way, right? It's complicated in physics. The best theory to describe what the data was telling us, right? So that the universe was expanding, not as galaxies, as pieces of shrapnel from a bomb, but that the space itself was stretching and carrying things along with it. And that the universe was hence very hot and very dense, close to the beginning. So it's a very hot primeval soup of particles that cooled off, and then all sorts of structures started to emerge in time. So that's the beautiful kind of narrative of the Big Bang model. So we're in the mid-60s, early 70s right now.
Right. And, Marcelo, how far back? I forgot the number. What is it, like 10 to the minus 11th of a second? That basically the data that we get from particle accelerators allows us to go back in time to, like, what is it? Was it 10 to the minus 11th? I forgot the exact number of a second.
About 10 to minus 12, 10 to minus 11. So 1/3 of a second, which, you may think, oh, that's almost like a ridiculously small time. And you have to say, it's ridiculously small for us, for human scales, but for a particle, that's a long time. Just to give an example, a photon, a particle of light, can go across the diameter of a proton, the thing that's inside the nucleus of an atom, 1 trillion times in a trillionth of a second. So it's an eternity for a photon, okay? So you can't really think in terms of, oh, it's so small, it's small to us, but not for the things that actually existed at the time, which were the elementary particle physics, elementary particles of matter and radiation.
So the important thing is that, okay, so, and this is actually on some level still true today, that where we have data, where we have data about the standard model of particle physics, which is the stuff we're going to pour into space-time, right? The standard model of the expansion of the universe. General relativity gives us the expansion of the universe. We're going to pour the standard model of particle physics into that. And that is good. That takes us back to 10 to the minus 11th of a second. And I think as we're going to start talking today about the problems that begin to arise, the problems that we are at now when you try and go further back and you start extrapolating that, perhaps too far, or in ways that really take us into what we call the blind spot. So I just wanted to say that's sort of where we're at and that we can pick up on now.
Right. So I think we also wanted to have either or both of you say some things about dark matter and dark energy and what's going on with those constructs in cosmology before we dive into the blind spot discussion.
Right. So let me do dark energy and dark matter, because what we're going to talk about is the stuff that got added, right, to cosmology after that 1970s period. And then, Marcelo, you talk about inflation, right? So if we want to get to what is now called the standard model of cosmology, the modern standard model, we got to add those things. We got to add dark matter, dark energy, and inflation. Okay, so dark matter is this idea that if you look at things like the galaxies rotating or the motions of material, larger aggregates of material in space, or even other kinds of cosmological data, what you find is that the luminous matter, the stuff you can see, does not account for the behavior. So for example, say rotations of galaxies. We see galaxies spinning, but they're spinning too fast if the only matter that was there was the stuff that is producing light. So it was from this and that kind of data, the galaxy data and other things, that led to the idea that there must be a large component of matter in the universe which is invisible, which does not interact with photons. So that is called dark matter. And it turns out that if that is true, then it's actually 90% or more of the matter in the universe, of the actual matter in the universe, is this dark matter, this invisible matter. So that, and now you've got to add to your cosmological models, not just the stuff you can see, made out of what we call baryons, made out of protons, neutrons, etc., and electrons too, leptons. But you also now have to add this stuff called dark matter, which we have no idea what it is. And since proposed kind of in the 70s, we still have
no. So let me just give a little bit of the history, which is kind of wild. So actually in the early 1930s, I think 1933, this Swiss-American astronomer Fritz Zwicky, right, at Caltech, he was using the same telescope, I think, that Hubble used to discover the expansion of the universe. And he was looking at how galaxies in clusters of galaxies, right? So galaxies are big things, but because they're so big, they have a lot of mass. And that means that they attract each other and they form these clusters, like this big sort of like, think of a bunch of bees, buzzing around. And he could use redshift to calculate how fast those galaxies were moving. And he says, well, they're moving because, they're being attracted by the masses of all the other galaxies. But when he got the speeds, he got speeds which were much higher than he would have calculated with the masses that could, as you said, that would shine. So he inferred that, there is this thing which is not shining, some kind of dark matter that is attracting those galaxies and making them move at much higher velocities in these clusters. So it has a really ancient history in that sense. Like it started with this guy, and then in the 1980s, I think Sandra Faber was the one at Santa Cruz, University of California, Santa Cruz, that was mapping the speeds, the rotational speed of galaxies. And she found that the stars in the periphery at the edges of the galaxies were rotating much faster than they should, if only it
was Faber. I'm sorry, I'm going to have a brain fart. Somebody in the comments, no, because we're naming a telescope after her. It was another amazing woman astronomer who was like one of the few women in the field back then who was willing to go up against the men, had this radical idea, but I don't think it was, but okay, let's just leave that.
But the point is that, so there is more matter on the outside that was not shining, and that was where the dark matter came back, right? So first as a local thing, and then in the clusters of galaxies, and then people use gravitational lensing to show that, right? So if you have a source of light really far away, and it's shining light, and this light goes across a bunch of galaxies in a cluster, the light gets deflected. I know my hands are all over the place here.
No, I'm laughing just because we had said in our outline that we were going to kind of zoom through some of this, but it's always so exciting. This is what happens when you talk to scientists. Like, no, wait, this is really cool. We got to go.
I know. I mean, but because matter bends light, right? So these things are bending light, but then again, the bending of the light creates these beautiful effects called Einstein rings, which are called Einstein rings because the son of a gun also predicted that this could happen. And it was found, right? And by reverse engineering this sort of distorted light, people could infer how much more dark matter there is in these clusters, which is like spectacular. So yeah, dark matter, sorry.
Right, so it goes back. And so there's multiple ways but the important thing also to note that it is now 2025. We have done lots of search. This is just a note. We've been doing like deep underground searches for dark matter. Like what kind of particle is it? And we still don't know. We still there's zero. And so there's some people are beginning to get sort of like, are we ever going to discover what this stuff is? So there's a whole other story there, but let's not go there. So let's just add. So there's dark matter. And then there was dark energy. And dark energy comes from the discovery in 1999 that the galaxies are not just expanding, not only is space just, coasting apart, stretching, but it was actually accelerating. The rate at which the universe is expanding is actually.
Can I say one thing? I think I
Sure.
remember the name of the woman astronomer was Vera Rubin.
Vera Rubin.
Yes,
Yes, there we go. Thank you, Vera.
My mistake. Yes. And I did not check on the internet, folks. I didn't. It was just verified there. But
Neuron,
boom,
yeah.
So Vera
Vera Rubin neuron. So when we get to Evan's stuff, it was the Vera Rubin neuron that fired.
just went, exactly.
Yeah,
So,
good you got it. It's important not to mix those ones up.
yes.
But she
yes.
was
Sorry,
amazing. I mean,
lady.
there are these certain women astronomers. I mean, they all were because they had what they had to fight against. But particularly,
exactly.
like, who were taking these radical Jill Carter in SETI is another one, who were willing. Like, not only was it hard enough for a woman even to like get heard in the room, given the way the men were, but who took these radical stances, and were right. So anyway. Okay, so the dark energy comes from this recognition in 1999 that the universe is accelerating in its expansion. And so what that means is there must be some kind of anti-gravity force. We talked a little bit about Einstein's original model for the universe where he put in the cosmological constant, which kept everything from contracting. So the dark energy, we don't know really what the dark energy is. Is it the cosmological constant? Is it something different? There were recent results that pointed perhaps to that it's not a cosmological constant. Either way, turns out that most of the universe's energy is dark. Now, we're going to come back to this idea of like all this dark matter and dark energy, which is just another way of saying like, I have no idea what it is. All I can see is the luminous stuff, and I see the luminous stuff behaving in a way doesn't make sense to me. So along with the dark matter, there's also this dark energy, as we were just talking about. And the dark energy it ends up is most of, if you do a tally, most of the energy in the universe, overwhelmingly. So it turns out that only 4% or 5% of the stuff in the universe is not dark, is the stuff we actually see and directly interact with. And as we're going to get to eventually, the idea that all of this stuff is dark may actually be pointing in some other directions. But right now, just to close this part off, and then Marcelo, you take inflation for 5 minutes. There's dark matter, dark energy. Those are the things that we now have to add to the standard model of cosmology in order to account for the data that we have. So Marcelo, now inflation.
So basically the idea then is, and this is coming back to the early 80s, 1981, Alan Guth was a postdoc, I think, at Stanford when he did this. There was this problem with the Big Bang model. So the Big Bang model, even though it was very good and widely accepted, it had some issues because, for example, it couldn't explain certain properties of the universe. One of them is that the universe could have 3 different kinds of geometry according to the theory of general relativity. It could be flat, meaning like flat like a tabletop, but in 3 dimensions, of course. We're not talking about time right now, just about the geometry of space. It could be curved like a ball, right? But not the surface of a ball, because the surface of a ball, again, is a 2-dimensional space. You just need 2 angles to locate any point. But we live in a 3-dimensional space. But it could have the spherical geometry, or it could have what's called an open geometry, which is more like a horse saddle, right? A horse saddle, it's a funny thing because it's kind of like in the direction of the horse, it curves up, but along the legs, it curves down. And this is called an open geometry. And if you draw a triangle, remember from your high school, folks, a triangle, if you add the angles of a triangle, you get 180 degrees, including geometry, flat geometry. But if you do that on the surface of a sphere, you get more than 180 degrees. And if you do that, so that's the closed spherical universe. If you do that on the surface of a saddle and a horse, you get less than 180 degrees. So the laws of geometry change according to the shape of the geometry. So what people were measuring about the geometry of the universe was that it looked incredibly flat, right? And nobody really could figure out why. If you look at the model of the Big Bang and the equations, that comes in as a constant K, actually we use a K, where if k is 0, it's flat. If k is plus 1 is a sphere. If k is minus 1 is a satellite. And we don't really know what number to put in, but it looked like from the data that k is equal to 0. So the question is how to explain the flatness of the universe. Okay, so that was one question. The Big Bang wouldn't explain it, you just put it by hand. Okay, and physicists always want to get to the, as deep as they can in trying to explain why things the way they are, right? So just putting it by hand was not good. You want to kind of actually know if there was a physical reason for the universe to have a flat geometry. So that was one thing. The other thing is called the horizon problem. I'm only going to talk about the flatness and the horizon problem because that's all that we need right now. So the horizon problem is, if you remember from our previous podcast, we talked about the microwave radiation, the cosmic background microwave radiation, which is when electrons and protons finally got into their embrace that became hydrogen atoms, and photons started to, they lost the love triangle and started to stream freely across the universe. And this radiation is still around us, right? I know, poor photons, right? I mean, but, and this radiation is around us, and you can actually calculate that in a cube of about a centimeter side, there are about 400 photons coming from that time in the universe, which is at about 400,000 years after the Big Bang. Okay, so that's that. Now, why is this interesting? Why is this a problem in cosmology? Because usually for things to have the same properties, they have to interact with one another. And you can associate the energy of these photons to a temperature, right? So hot photons, high temperatures, cold photons, small temperatures or low temperatures. And if you point your antenna and you look at photons in one direction of the sky and you measure that temperature, and you point it on the other direction of the sky, so like two directions like this or like that, they have pretty much the same temperature to 1 part in 100,000. And there was no time in the 400 billion years that the universe has existed for these photons to communicate with one another. And certainly at that time, 400,000 years after the Big Bang, to communicate, to interact, and regulate that temperature so that everybody has the same temperature. So the question is, how the heck did that happen?
Can I my favorite metaphor for this? It's like opening up the newspaper and finding that every city in the world has exactly the same temperature that day. It's exactly 72.345 degrees everywhere on the planet. You'd be like, what is that? That's just an accident? There's no way all those places could have had the exact same weather. So that's what every different part of the sky has the exact same temperature, and they didn't have time to interact to smooth out. So sorry, I just wanted to throw that in, but that's my favorite.
No, that's great. It's sort of like the whole universe is in a single oven, right? So it's all being baked to perfection at the same temperature. And the question is, how the heck did that happen? There was no time. Light is fast, 300,000 kilometers a second, but it's not instantaneous, and it takes a while. And so that was a big mystery. So these two things, right? Again, the flatness of the universe and the temperature of the microwave background to 1 part in 100,000, right? And so Guth had this spectacular insight, and he said, well, maybe what happened is that when the universe was really young, I'm talking about really, really, really young, if you think 10 to minus 12 seconds, right, which is 1 trillion, it's early. Think again, because this thing is way, way closer to time equals 0. But he says, let's speculate that the physics of the time allowed for the conditions in the universe to be such that the universe could expand for a very small amount of time, but incredibly fast, exponentially fast. So this stretching of space was super fast. And then what happens is the following, is that, first of all, think of this, the surface of a sphere, a ball, right? So you have a little ball, right? And you look, and it is very, very curved. So you take a little square on the surface of the ball that is very, very curved. Now inflate that ball to the size of the size of a building. Well, clearly, that little square that was very curved is going to be flat or close to flat. So the idea is that the same thing happened to the universe. It inflated it so fast that what was very curved in the beginning became flat now. So that solves the flatness problem. And for the horizon problem, which is really the temperature of the photons, the same thing. Photons, if they weren't very close to one another when the universe was a baby, right, they could interact with one another, arrange their temperatures, and then poof, when the universe expanded, they're all part of the big family that, yes, we are the same temperature kind of thing. So inflation in one single swoop, right, sort of solved all these and other problems also, which we don't have to go into detail right now. But the thing is but it did it by asking that the physics of the universe at 10 to minus 35 seconds, which is ridiculous.
Right. We're at 10 to minus 12, and now we're at 10 to the minus 35. Huge extrapolation backwards to crazy new energies, but we'll get to that. Sorry, I didn't mean to jump in.
Yes. So basically, so it's a trillionth of a trillionth of a trillionth of a second after the Big Bang. The universe went through this super fast expansion and
then stopped.
And then went back into the normal expansion rate. And in fact, there's a ton of stuff that goes on in here. Some people now say that the real Big Bang didn't happen until after inflation, because what happened then is that, how the heck did this happen? Well, apparently there was a field, some energy matter field across the whole universe that had the right temperatures, the properties working again as negative pressure, kind of like a cosmological constant. But you can think of the field as a little ball on the hill. Let's say that my forehead, like my bald forehead here, is the top of a hill. The field is here. It's going to go down because it wants to go to where there's low energy, right? And as it's doing this, the universe is dominated by the energy of this field. And this field with this property has negative pressure, which allows the universe to expand incredibly fast. The difference between this field going down my forehead and the cosmological constants just stay put. It just stays there. It doesn't change values, right? So eventually the field is going to go, and then it's going to get to the minimum, and it's going to oscillate a little bit about the minimum. As the field does that, it creates a gigantic amount of energy and particles. And those explosive particles, it's called preheating. It's where the explosion of creation of new matter particles exists. And that's what people sometimes call, this is the real Big Bang, not the time equals zero Big Bang. Okay, because you can't go back to the history, but that's something we can discuss in more detail. So that's what inflation does. The price it asks us to pay is to assume that there is such a field early in the universe that has the right properties to be on top of an energy hill so that it can create this fast expansion for the universe and solve the flatness and the horizon problems. Back to you.
All right, so that was sort of, so the modern cosmology is what we call the standard model, is inflationary expansion, plus dark matter, plus dark energy, plus the standard model of particle physics, right? That is what we now call the standard model. And it's turning out that that model is admitted by many people is in crisis in different ways, right? Again, everything from 10 to the 11 of a second onward is in pretty good shape. But there are problems that are arising, and some of them go back to, and this is where we're going to start hitting the blind spot. Some of them go back to the whole idea of be able to describe the universe as a whole with a single theory. So let's just touch very briefly on the problems, some of the cosmology problems, and then we can come back to like sort of the blind spot stuff. So let me just very quickly go. One of the real problems with cosmology right now is what's called the Hubble tension. Is that if you look at the expansion of the universe, what's called the Hubble constant, the thing that's telling you how fast the universe is expanding, and if you look at ways of measuring that using what we call local measures by measuring things that are relatively close cosmologically, you get one value. And then if you use things from the early universe, you use basically stuff from the cosmic microwave background, where there's a lot more model dependency, you get a different answer. And it used to be when we were young, we'd go to meetings and people would say, there's a Hubble tension, but don't worry, it's within the standard, it's within the error, the difference is within the error, and it'll get better, we'll reconcile these. So now it's decades later, And the differences have gotten worse in a way. The error bars have shrunk to the point where these are two different values. If you use the cosmic microwave background to get and the models, cosmological models from standard cosmology to get your Hubble constant, you end up with a different value than if you use local measurements. So that's called the Hubble tension. It is not going away. The other problem of a bunch of problems that has come up is that with the James Webb Space Telescope, the whole idea of this standard model of cosmology gives you a timeline from inflation onward for things to happen. It's kind of like a play. This happens, then that happens, then this happens, and that happens. And one of the scenes is the formation of the first black holes and the first galaxies. And it's turning out that in many ways that is happening a lot earlier. We're seeing fully formed galaxies and black holes much earlier than we would have thought. Now that one may be reconciled by tweaking the knobs on the models, but it just stands that way. So there's been a number of things sort of showing up in cosmology recently in the data that is pointing to there's really something wrong with some parts of this standard model. And so then, Marcelo, I just want to turn to you to sort of also talk about the problems with inflation, particularly the fact that it's many models, it's not one model, and then also eternal inflation in the multiverse, that you're sort of stuck with the multiverse if you want to believe inflation.
So how does this work, right? So we have a model of the universe that has three basic ingredients, as Adam was saying. Let me just recap this stuff so that we're all together in this. So you have ordinary matter, the stuff that stars are made of, and you and planets, etc. And that's about 5% of what's out there. And then you have dark matter, which we think it may be elementary particles of some kind that do not interact with light of any in any shape or form. Some models kind of try to do that, but it doesn't quite work. Or they could be little lumps of stuff that also don't shine, right? I have a model about that actually. And that's about 27 or so percent of what's out there. And then the rest, about 68% or so, is this so-called dark energy that we have no clue what it is. We just know that what it tells you is that about 5 billion years ago or so, which is kind of funny because it's about the same age roughly as the solar system. That's when the solar system appeared. We call it the coincidence problem. Why is it that the universe decided to accelerate its expansion more or less at the same time as when the solar system was being formed? So there is something to be considered there, but that thing is 68% of what fills up, let's put it that way, the volume of the known universe. And so these are the three ingredients, right? And then you have inflation, which is assuming that we can, and here we go, let's talk a little bit more about philosophy, because I want to talk to Evan about this whole stuff, because it really is a fight between ontology and epistemology here, because what's going on is that we measure stuff at CERN, okay, which is telling us, look, these are the material components that we know exist. So you have quarks and leptons. Quarks make up protons and neutrons. Leptons are electrons and a bunch of other stuff. And those 12 elementary particles are also the neutrinos. And then there's the Higgs, right, which was discovered recently-ish. And so you have those particles, and we have some confidence that the way we model the way these particles interact works quite well, which is the so-called standard model of particle physics. This model, especially the Higgs, is what we call a scalar field. So it's a field that doesn't have a preferred direction in space, sort of like temperature. Temperature is also a scalar field. You can go with a thermometer and you can measure the temperature in a room, and each point in the room is going to have a temperature, but it's not going to have a direction. Oh, it's moving, in that sense. So it's not a vector field, it's a scalar field. Okay, so Higgs. So the idea that people have had, and I'm spending a little time on this because that is essential for what we want to discuss, I think, is that let's then assume that as you go to earlier times in the history of the universe, there will be other scalar fields that we don't know about yet. But given that the physics that we have at the electroweak scale is so successful, let's extrapolate it by about about 20 orders of magnitude or so to higher energies and say that there will be scalar fields there. And if there are, and if they have the right energy profile, like the one I was talking about, my forehead that goes down like this, then they would dominate the energy density of the universe and make the universe expand extremely fast. So you are taking knowledge at an energy scale, which is the energy scale that we use in the laboratory.
And the minus 11th or 12th, the one we have data for.
Right. Which is, when you do this E equals mc squared kind of calculation, we can always talk about energy and mass, forget about the speed of light. And so it is basically what we can do in the laboratory. It's a good kind of parameter. It's about the energy equivalent to 1,000 times the energy in the mass of a proton. It's 1,000 giga electron volts, okay? So 1,000 times. The energies that we're talking about when we talk about inflation, and I'm not even going beyond that, let's just stay there, is 10 to 15. So you go from 10 to 3 GeVs to 10 to 15, so 12 orders of magnitude. And we're saying, well, at that time, possibly another one of the forces of nature called the strong force could also be unified with the electromagnetic and the weak, and that's called the gut theory, the grand unified theory, right? And let's try to construct a theory similar to the one that uses a Higgs. And maybe a field like that, or perhaps a cousin of a field like that, was the one that did inflation. So we are building models.
So that's what's called the inflaton. Whatever field drives inflation is called the inflaton. And the important thing to understand is we have no idea what it is. It's a hypothetical field that does what you want it to do in order to get inflation to solve your problems.
Exactly. So then the question becomes, right? I mean, it's okay to speculate. We have to speculate. Theoretical physicists do speculate, right? But what has happened, and this is where I want you to jump in, Evan, is that the speculation became almost dogma in the community, right? Because it was such an appealing idea, right? Such a beautiful way of dealing with questions that we had about the Big Bang model, that there was a jump here, and what was speculative became sort of like the lay of the land, right? And to what extent is that good science or just bad philosophy or both, is something that I think would be very interesting for us to discuss right now.
Yeah. So, I mean, from my perspective, and of course, I'm not a physicist or an expert on any of these things. I mean, it seems perfectly reasonable to think that that there are conditions in theorizing or in model building where you are going to extrapolate, and that enables you to test the models in various ways, maybe test their limits or test their, further applicability. And absolutely, that's to be expected, and that's fine. The thing that I notice is when those models then become reified into ontologies, where the idea is that, well, this is really, we have some confidence that this is how things are in themselves in some model independent sense. And then moreover, and not all physicists do this, but some very prominent physicists do this, they say, and this enables us to, really get a grip on these kind of fundamental questions like, why is there something rather than nothing? There was an exchange some years ago in the New York Times between, physicists and philosophers about, physics. And I think actually Hawking says this as well in his very dismissive attitude towards philosophy. He says, well, we physicists have basically answered the philosophical questions. And there's sort of two mistakes there from my perspective. One is this reification of models, which are always epistemological devices, tools of knowledge. They're knowledge tools. So reification of those into being, into how things are, that's what we call in our book, following Husserl, the surreptitious substitution of a tool for an ontology. So that's one mistake. And then two, it betrays a misunderstanding of what the philosophical questions are actually asking. So if you were to bring back, Aquinas or Averroes or Avicenna, these magnificent medieval philosophers in the Christian and Islamic traditions, and say to them, well, we now have an answer to the question of why is there something rather than nothing, and here's what it is, they would look at you as if you didn't understand the question. I mean, because the question is actually a question about given that there is contingency, in other words, in some sense, things could have been otherwise, what is it that grounds the contingency? And if you appeal to something that is itself contingent, like laws of nature, which could have been otherwise, presumably, then you're not giving what in their eyes is required for an answer, which is something that has to do with necessity. Now, for them, the necessity resides in, the divine, and we could argue whether, that follows. But in any case, the question has a logical structure that just is not being understood, from the perspective of the physicists who are kind of reifying these models. I mean, to put it another way, the idea that the medieval philosophers were working with, and you also see it in Leibniz, you see it in a number of philosophers, is that nothing within, that is inside the cosmos or nature, contains the ground of its own being because it's contingent, could have been otherwise. The cosmos or nature requires some ground of its being. And so that ground must be something that has a necessity to it that isn't the contingencies within the framework of the cosmos. So now you can say, well, that's not a question that can be answered scientifically. It would need to be, if it's answerable at all, it would need to be answered in a philosophical way. That's maybe a different kind of discussion. But the point really is that that's a different, logically speaking, that's a different kind of question that models don't really enable you to answer.
Yeah, and I think this is one of the things, this is the first place where, for people listening, is to understand one of the thing, our main points here is that what you see, by the way, the book was a Universe from Nothing by Lawrence Krauss.
Yeah, right.
It's David Albert who wrote that. It was a front page review of the book that was the most searing critique. Yeah. It's like the review of your book that you never want to get. It's like basically this guy cannot think his way out of a wet paper bag. It was just devastating.
Yeah, it's a pretty devastating review. Although, as they say, a bad review is better than no review.
I would not. I would rather not have I'd rather have my book sink into oblivion than get that review. And it was this point that we often see with especially when it comes to cosmology, physicists who don't have much philosophical training, saying like, oh, I don't need philosophy because I've already answered these questions with physics. And you can see in Krauss's book where he makes these the regular derogatory statements about philosophy, not recognizing he just made a bunch of philosophical statements. And you see this again and again. And it's clearly some physicists who are very philosophically astute, and that's great. But often in this, because it's cosmology and because it touches on those deep issues of ontology and even bumps up against theology and religion, physicists making these wild claims that their 20 order of magnitude estimate extrapolations show us, prove to us that the universe is a rational structure and all the questions have been answered. And I think that's really where we're going to get started now for the next 20 minutes and come back to at other points about the way cosmology gets deployed that way in service of what we call the blind spot philosophy. Cosmology, which really now is actually running up into, when it comes to that early universe stuff in particular, is running up against some fundamental problems, is used as a kind of cudgel to say science can explain, or this kind of science can explain everything. We don't need any philosophy. We don't need to think about our own place in the universe as observers because, we basically got the God's eye view of the entire universe right here.
Right. So let me ask both of you as physicists something. So it seems to me that, if you were going to say we could have a theory of everything, that everything, let's say within physics terms, everything is going to be, you're going to treat the whole universe as one dynamical system. But what sense can that possibly mean or have, given that you can't stand outside the universe and specify the boundary conditions, the initial conditions in the way that you do for dynamical systems when you make a model of something in dynamical systems terms. And moreover, you are inside and are part of the universe. So how are you going to recursively build yourself into the model that's supposed to be a model of everything? It seems immediately that it just violates the principles of scientific intelligibility.
Yeah, I couldn't agree more. I actually wrote a whole book about this.
Okay, there we go.
The knowledge,
right.
and even another one before that. I argued that it is philosophically wrong to consider even remotely the possibility of a theory of everything. right? And by the way, let's be qualitative here. So a theory of everything means, when physicists talk about it, they don't mean the theory that is going to tell you who is going to win the next American election. They mean the theory that is describing how the fundamental material and how fundamental components of reality, physical reality, interact with one another, right? Exist and interact. Which ones are those and how they interact? And the way they do this is by assuming that there are four forces of nature, right? The gravitational force, the electromagnetic, the weak, and the strong nuclear forces. And that it is possible to come up with a theory that very early on in the history of the universe would show that those four forces that we see them now as separate interactions actually behaved as a single force, a single interaction, okay? So that's what unification means. It starts from oneness, and then it goes on splitting. Exactly. I just implicitly said, but then we had the angel Adam come in, and, which is a great name for that, by the way, Adam. You're the first man, dude. So hey,
I'm no angel, honey.
But so the first point is that how the heck do we know that there are only four forces? Where's that coming from? I said, well, that's what we measure. Yeah, that's what you measure now. 100 years ago, there were no four forces, right? 100 years ago, there were two forces. It was electromagnetism, which was a unification there, and gravity. And as we improve our technology, right, one of the things that we can and must learn from the history of science is that new tools create new visions of reality, right? They are what we call reality amplifiers, right? So there is no way anyone in the world can rule out the possibility that exists, that there is a fifth force out there, or sixth or seventh. And then your theory of everything can never be whole, because you can never be 100% sure that there isn't something else hidden. For example, people talk about, is the Higgs fundamental particle, meaning you cannot break it down into anything, or could it be actually a composite held together by, who knows, maybe a new force of nature that we don't understand yet? And dark matter, we are not finding it, right? We've been trying to for many, many decades. People use a whole new way of thinking about particle physics called supersymmetry. Well, it was invented, let's put it that way, in the mid-70s. And it predicts basically that each particle of nature, like an electron, a quark, would have its supersymmetric partner. So an electron will have a selectron, a quark will have a squark, a photon will have a photino, a gluon will have a gluino, et cetera, et cetera. And people have been desperately looking for those things forever, for at least 4 or 5 decades, and we have found nothing, right? So,
Marcelo, can I just jump in just to amplify that point just for a second?
Yes.
And this is really important, because so much of, if you want to go back in time and have your theory of everything, have your cosmological model, which sort of serves to, embody this triumphant vision of science explaining everything, then, to recognize how much that has gotten in trouble. The supersymmetry, the idea that there was going to be all these other, you could extend the standard model with supersymmetry, was this dominant idea for 30 years, like thousands and thousands of papers. Everybody expected the LHC to discover it. Like after the Higgs, that was coming. Like we discovered the Higgs, and then we instantly start finding evidence for the supersymmetry. It's clear it's not there, right? That is what people talk about, the crisis in fundamental physics, the crisis in particle physics, is that it turned out it was a ghost. It was something people wanted to be true, and it wasn't true. String theory, which of course everybody's heard of, is actually supersymmetric string theory. It doesn't work without the supersymmetry. So unless you do other things that make it so complicated that it's no longer even useful. So I just want to amplify this point, that why foundational physics is in so much trouble, and why this is trouble for the early universe, is these things were all the central to this idea that physics was about to be finished, or at least we get the full early universe, we get the full model of a theory of everything. And our whole, both Marcelo and my entire career has been sitting in front of talks with people like string theory real soon, and it has not worked out. It has just not worked out. We can talk about the culture of that has led to that and the problems that has led to, but the fact of the matter is it has not worked out, and where do we go from there? So I'm sorry, I just wanted to
No, this is super important because these are all my colleagues that I grew up with, a lot of them. My PhD was in string theory. I wrote gazillions of papers on cosmologies in 10 dimensions because apart from supersymmetry, string also requires that you live in many more than 3 dimensions, or they exist, right? But to me, what's really fascinating is that the whole notion of supersymmetry is more of a sociological problem in the community of theoretical physics, high energy theoretical physics, let's be clear about that, because you can't kill it. You cannot kill it because the way those experiments work is that you collide in the case of the LHC, the Large Hadron Collider at CERN, you collide protons against protons. Their energies are gigantic, and because of E equals mc squared, the energy of those collisions create a bunch of other particles. And the hope is that out of that soup of particles that is created from the energy of the collision, there'll be new particles which are supersymmetric particles, right? And so I have a bet actually with Gordon Kane, who is a professor at the University of Michigan. He's Mr. Supersymmetry, one of them. And I said, there is no way we're going to find it. And we've had this bet, oh my God, since, I don't know, for at least 15, 20 years. And it was it was a bottle of 18-year-old Macallan, right? And a few years ago, that's a good, and a few years ago, I said, Gordy, give up because, they're not finding. That is not. And what he says is, well, when they boost the energy of the collider a little more, maybe it will show up. And that is a very interesting point because when do you give up an idea?
Right.
When do you say, sorry, folks, my whole career, I was working on something that didn't work out, and it's complicated. It's emotional. It's an emotional thing, right? Because how do you deal with that, right? And you always have maybe, if there is a new collider that's going to have an energy 1,000 times higher than CERN, that's where the supersymmetric particles will be. And so it becomes a technological problem. It becomes an economical problem. Can we even build machines with that energy? And so it is a theory that in principle cannot be killed because you can always come up with a new model, tweak the mathematics to have heavier and heavier supersymmetric particles so that you just can't find it. So when people say supersymmetry is dead because the LHC hasn't found it, they're also usually talking about the simplest supersymmetric models, right? So it's a very interesting mix of sociology, economics, and really feelings, of people like, what do I do here?
Right. And it's not like, it's not like anybody did anything wrong, right? I mean,
you have to speculate.
They dedicated their lives to an idea, which seemed like a good idea, and it didn't work out. But if there was something that was wrong, it was that particularly in the media, particularly, the way it got, certainly, especially string theory, got sold as this theory of everything, as this, again, the God's eye view. One of the things we're arguing against in the blind spot is that science gives us this God's eye view, this perfect view without us. And this, Evan, I just want to also address your question in 1 second briefly. But that was really the problem with, so many books about, the beautiful fabric of reality. We're actually finally going to find the ultimate reality, which we were told that's what physics is going to give us. Our whole point is there is no ultimate reality without us. You can't tell that without us. But I want to speak to this very briefly because we don't want this to go on too much longer. Evan, you asked about the idea of the universe from the inside, right? One of the tricks that got played to me in the physics community in this was when I was young, there was this thing called the anthropic principle, right? As a young physicist, it was the idea that you can use our existence as observers to infer certain properties about the universe. And when it first came out, everyone was like, It's a little weird, it seems like tautology, but but in general, most people were like, I don't really think that's a good way of doing science, the anthropic principle. And then you get string theory, and then you also get, we haven't really talked about eternal inflation. One of the problems with inflation, if I understand it correctly, is that in general, you can't have inflation without having the part of inflation that works on our universe being just one part, where there's other bubbles of reality, that are also inflating. You end up with a multiverse, like the idea of the multiverse, of this beautiful science fiction idea of, infinite numbers of universes that are kind of parallel, they're like us, but they're not like us. But that sort of inflation forces you towards a multiverse, an infinite number of unobservable universes, right? And so there was something that happened with string theory, which is the idea of the landscape, where it was recognized that string theory would never predict our universe. It could at most predict like 10 to the 500 universes, and ours would be one of them. And then at the same time, inflation is giving us this idea of the multiverse. And suddenly the anthropic reasoning, everyone's like, oh, that's cool. Anthropic reasoning. Yeah, there's an infinite number of universes. Ours just happens to be the mediocre one. Now we can use the anthropic principle and the idea that there's an infinite number of unobservable universes to infer properties of our universe, right? And so what should have been a bug in the theory, and string theory and its 10 to the 500 universes, suddenly became a feature. And what it was is, Evan, it's exactly what you're talking about. What we did was, we took our one universe that is very hard to explain why it has its properties, what's called fine tuning, and suddenly it treated the whole universe as if it was just like statistical mechanics. There's an infinite number, there's an ensemble of universes, and now I can talk about average properties of universes. And to me, that was always like a real bait and switch, where like when I grew up as a physicist, anthropic reasoning was looked at suspiciously. And suddenly these two theories that everybody wants to be true who's working in the field predict multiverses. And then suddenly it's like, oh yeah, the anthropic reasoning, it's great. And what it does is it literally takes this problem that you're bringing up of like, how do we describe the one universe we're in and our place inside of it? And it says, no, don't worry about that, because there's an infinite number, there's an ensemble of universes, just treat it like statistical mechanics and an infinite number of experiments. So I always thought that.
Can I say one thing to complement that? Because this is a very interesting, again, philosophical point, because when I was doing my PhD in the 80s, string theory, if it worked, would have one solution to the equations of string theory, and that solution would be our universe with its four forces, unified, etc. So that was beautiful. That was the uber Platonic expectation, right? That you could actually use geometry and mathematics and fundamental physics to describe the wholeness of reality, everything. Exactly. So it was a very wow, of course, in my 20s, yeah, of course I want to do this shit, because it's so cool, right? And but then what has happened is that with the failure of not finding, there is no such one equation because of so many other problems with the structure of the theory, that you go into this multiverse where you have a string landscape, which is what Adam was talking about, right? And landscapes with little bumps, little holes in it. And each one of these holes is a potential possible universe with different laws of nature, different values of the fundamental constants, like the mass of the electron, the strength of the weak interactions, whatever. And so our universe goes from being the solution to being a statistically irrelevant possibility in this ocean, of gazillions of universes that, by the way, you cannot know exist because you cannot get information from those other places. So it's a theory that from its very foundation, right, from this very way of being built, cannot be empirically tested or validated, right? Some people say, well, if there is a universe outside of ours and it hit ours, you would leave a scar on the cosmic microwave background. I'm like, by the way, they calculated what kind of scar that would be. They didn't find it. But I'm like, really? Is that the only thing that could cause that scar? And so it becomes a very interesting shift right? In the ambitions of
cosmology. Yeah. So I'm going to suggest, because we're getting towards the end, that Evan, you take us out, So we sort of described, especially this problem of the post-empirical, people call string theory, it's post-empirical because it's so beautiful, it has to be true, which makes my head explode. But Evan, I'd just be interested, your opinion, sort of, we described the problems, and as a philosopher, how do you take this in?
Yeah, so, I would say, we've sort of picked on the physicists or some of them. But, this is a problem, this dynamic is a problem that we see in other areas of science. So it's a problem of hype and reification. So we see it in biology with the idea that now we're really going to understand life because, we understand the genome, or we're really going to understand intelligence. This is actually current hype. We're really going to understand intelligence because we now have these incredibly powerful large language models. So we see this kind of over and over and over again, increasing sophistication of models within certain dimensions or parameters, and then a reification of them and grand claims made about them. So this is something I think we'll return to a lot in our discussions when we, look at how this plays out in neuroscience, how it plays out in biology, how it plays out in, cognitive science and artificial intelligence. Eventually we'll bring other people in to talk about this. So it's, it's not just us. But this dynamic that we've seen in cosmology that we've talked about, increasingly sophisticated theory, but increasing remove from, empirical application, we see this in other places too. So stay tuned for more of that.
And then hype saying like, this is it. We've discovered, we know what consciousness is. We know how this began.
Yeah, and the most important thing maybe, to end with is that the reason we're harping on this is because we care about science. This is bad for science, right? It's not an argument against science. It's an argument
we love science.
for science.
The opposite, right? It's the opposite. We're trying to kind of keep things where they should be and not like in a fantasy world. Exactly.
Thank you guys for joining us on this, and we'll see you in a week or two whenever our next one comes out.
Yeah. All right.
Bye.
See you soon.
All right.
Bye.
Bye, everybody.